All right, we can get started. Okay, that's going to work. That volume's going to work. Thanks. Okay, part two. This is going to be a little more technical for people who are here in the first part. I strongly believe that there should be a sense of what we call transferability in studio control room performance. Okay, you certainly need to trust your room, since basically you're making judgments. The only way you can make judgments in a room is if you trust what's coming out of your monitoring system, whatever that is. All the rest of the conversations are important. Delivery, multiple formats, multiple speakers, et cetera, but at some point we need some standards, and it's only going to get more complicated with immersive, no matter which immersive conversation you want to jump into. So I believe that to be true, and I think that my panelists would also believe that. Does that mean that the bagels aren't important? I mean, sure they're important, and maybe they're the most important, depending on the client. Same with the lighting and the vibe and the mood, and we can go on and on and on. For the next 45 minutes, we're just going to talk about this concept of transferability. It's an honor to, actually I'm going to just, again, take the easy road, show some photos, et cetera. Then I'm going to let the heavy lifting be done by a really dear friend and my partner and longtime colleague, Peter D'Antonio, Dr. Peter D'Antonio. And you know him, he's the inventor of founder of RPG, which clearly changed our industry. So all those kind of fluted little things in the back of 99% of all the rooms, he caused that to happen. So sorry. Way to go. And made a fortune doing it. Well, not really. Okay, but it clearly changed our studio thinking and our industry, and lucky for me, a change in his life allowed him to now become director of research of essentially our research company, which has gone through a kind of very strange path to now come up with what we consider to be some very, very interesting analysis and prediction software, which we're going to share with you. Started out as a low-frequency analysis tool. Low frequencies, for all of you that have studios and have small studios, is clearly the bane of everybody's existence. Managing mids and highs is not that difficult. I mean, it doesn't mean everybody knows how to do it, but at least conceptually it's not that hard. Figure out where the reflections are and deal with them. Don't make the room too big. Get your room symmetrical. You're already 80% there. Low frequency, this is very, very different. Commonly called standing waves or eigentone analysis, whatever. This is hard. And what started out as an intern project in our office became a research project, became a more complicated project. We and proved that the tools we were using were not really working after all these years, and we had to go back to ground zero and kind of invent a new tool. So we're going to share some of that with you. I want you to listen to some music for a few minutes. These are really songs that most of you know. I knew them. I knew all but one. And look where they were made. All made in or created in at least 4 different environments. Okay? Embarrassingly enough, I did not know this song. I got chewed out from some of the younger guys in my company. What do you mean you don't know who this is? Okay? Tom at Electric Lady. It's a great song.
He left no time to
We miss Amy, of course. But look where it was done.
kept his way with his same old safe bet.
Great mixing engineer, Manny. Works with Jimmy all the time. Bedroom studio. Who's the bedroom studio question? It's a great song. You could have made this at a Dunkin' Donuts. It doesn't matter. It's a great song.
Where do we go? Bring it down gently.
Seven different studios it's created in one way or another. Okay, my point is that this is not rare anymore. This is actually what's happening, and you just saw at least 2 people up here that make a living by taking stuff that's made in some way or another in at least one, if not more environments, and then being asked to make them, quote, better or different, and they're not even done yet. They then have to leave and go get mastered. Okay, so this term transferability, which is Peter's idea, this trusting of your control room, this accuracy, okay, has never been more important. I like the center term there. If you can't take the room out of the mix, you can't take the mix out of the room. Okay, so these are just some, we're just going to get going here. These are some studios that are accurate. Here's one that I'm not sure if it's accurate. In fact, I'm pretty sure it's not. Okay, and it's not because it's messy or the photograph is funky, okay? There's just no doubt in my mind that there's a console bounce. The speakers are a little bit too high. They're most likely very, very close. They're way too close to that back wall, so there's going to be some speaker boundary interference. I just grabbed this off the internet. This is just to make sure, just to prove a point, okay? What's sad when I see this, what makes me happy when I see this, is that somebody's mixing and making music. This is great. This is the democratization of our industry. What's sad is that this room could sound 100% better with a few moves. No money. You don't even need any money to make it sound better. Lower the speakers, put them off the wall, and put a little foam behind the speakers, and it's already going to sound better, okay? This is not a 5 tips on how to make your control room sound better talk. That's not what I want to do, okay? But it's up here to prove, just to sort of prove a point, okay? Whereas here, this is one of the first rooms that we did using the software. This was in the some of the early days of our software, which Peter will talk about. Just showing you some examples of studios that do sound really good, and they don't have to all look the same. As a matter of fact, the only thing that's common about the ones I'm flashing up here is that I had something to do with them. They're all supposed to be different, because it turns out that the vibe and the donuts and the lighting are important, okay? But they have to sound accurate, and you have to trust them. This is Boston Symphony Orchestra studio, okay? This is a 12.1 system, etc. So that's just to kind of get us in the mood. As I said, I have the easy job and Peter has the hard job, so I'm going to switch seats. And remember, you have to see the camera. So maybe move over just a little bit. And if you hit this guy, you can move forward on your own. Again, it's a real honor to know Peter for 40 years and be one of the designers that have always experimented with his new products, and my partner in this adventure.
Thanks for the trust.
Yeah.
So I like to think of this topic in the terms, if I were an artist, would I rather be painting on a blank canvas or a canvas that has some residue of some previous artwork? And the reason for saying that is that when we're mixing in a room, in a space, imagine the situation where a multi-track recording has been completed, and now, as people have been mentioning, it's going to be mixed in 3 different control rooms with the goal of the producer or the artist to make, as best they can, the same mix. Well, when you play those mixes outside the rooms, they're all going to sound different, because the acoustical signature of that room is going to be inversely impacted on that mix. For example, if the room is boomy, the mix is going to be bass deficient. If the room is bright, the mix is going to be dull. So as studio designers and optimizers, our goal, we're almost like sommeliers with wine. We are connoisseurs of audio, of acoustics. We need to make the room a control room. Now, what John showed you is mixing environments, but are there really controlled mixing environments? because what is done in that room is going to sound different when you take it out of the room. So our goal is to make the room as flat, neutral, with a natural ambiance, because engineers work in there for countless number of hours. And so to do that, we have to get scientific about it. What you're seeing...
I think we just want to go.
Yeah. What you're seeing...
So we're going to talk about the science of what we hear.
So in order to make the room neutral, and we hear that word neutral, all it means is that what you do in that room can be taken out of the room. It doesn't have the signature of that particular room. And so in order to do that, we're going to talk about three aspects of it. We're going to talk about the things that don't make it neutral. That is acoustic distortion from these four sources. We're going to talk about a design software that does its best to convert a room into a neutral room, and then using four metrics. In other words, when we get these four metrics right, we're going to consider that a neutral sounding room. Now think of it. Think of all the constraints that we have to deal with. We have to deal with the architecture, the geometry of the room. We have to deal with the acoustics. We have to deal with the aesthetics of the room, the vibe of the room. You know, what we're dealing with clients. So the client might not like an acoustical treatment. We have to deal with the audio, the console, the loudspeaker, the microphone. And then we have to deal with the art. And what I mean by the art is personal preference, the subjective impressions of the owner, mixing engineer, what have you. So with all of those limitations, we have to first be as scientific as possible, and we have to minimize the modal response. As John,
One thing.
Yeah.
Just go up to slideshow.
as John was mentioning, the modal response is the most difficult because these are very long waves. And so to treat them or to analyze them, we have to use wave acoustics. And what that means is there's a very complicated equation. It's called the wave equation. And we have to solve the wave equation. And the program does that. The second potential problem is the speaker boundary interference. All that means is that at low frequencies, a speaker is omnidirectional. And so the speaker boundary interference is essentially cone filtering at low frequencies. It's the combination or the interaction of the direct sound with the omnidirectional waves from the boundary. And then we get above about a frequency of 200 hertz, and we get into a more specular region where we have cone filtering potential problems which occur from the coherent interaction of the direct sound with specular reflections. And it's not enough to put up a 2-inch fabric wrap panel because you still have the cone filtering from the lower frequencies. And then lastly, what really is not much considered by many is poor diffusion. You may have a room in which the sound is not uniformly oriented, directed. You may have a diffuser that has a poor diffusion response. And so we're going to optimize all of those potential problems.
Can you hit the arrow?
Yeah. The first way that people normally address this problem with respect to low frequencies is using the dimensional ratios of the room. And just to say that is important, but it's many steps away from what we hear. Okay, we hear the frequency response, we hear the impulse response of the room. And so to do this, we generally use a formula that you see there. In the denominator, you have the length, the width, and height of the room, and the lowercase n's are integers. C is the speed of sound. And what that formula does is it calculates the location of the modes. Now, it determines that if the room is completely reflective, which very few rooms are, and if the speaker and the listeners are in opposite diagonal corners. Now that's not typically how we listen to music, but nonetheless, that is the extreme condition with which that formula is accurate. And so what you get is a distribution of modes. You get a location of the modes. You do not get any information about their energy. You do not get any information about the frequency response. And so over the years, many different researchers who are very accomplished acousticians. It started out with Bolt, and came up with the idea that let's make these modes equally spaced so that they really don't affect the mix as much as they would if they piled up and they were next to one another, because then they would couple the effect. Keeping with that idea of equally spaced modes, who's next? Loudon came up with a single metric, but again, for equally spaced modes, and they're all equally spaced modes. Loudon, Bonello came up with the idea that as you go up to a higher third octave, you don't want the number of modes to decrease. So you want the room to continue to get more exciting. Walker came up with a similar approach, but he did point out a very important thing, that these dimensional ratios are volume dependent. And then later on, Trevor Cox and I came up with a solution which I feel it really addressed the problem, because the metric that we used was the frequency response. Not the modal spacing, the frequency response. We used an image model to generate that, and we're going to talk more today about an extension of that. We didn't have the capability that we do have today. So we can begin this analysis by looking at the combination or the comparison between the dimensional ratio analysis and finite element calculation, which is a wave-based solution. It's as best as we know how to do.
I just want to interrupt for 1 second. So this equal spacing of the modes, which most of you should be familiar with, and for years I did believe in it, was what we stumbled on, and we were using this, continually using it, until basically we realized, and it was, I guess it was kind of an accident, that it describes, as Peter suggests, a situation that never happens, which is a speaker in a corner and a listener in a corner. That's never going to happen, okay? And we also discovered that you can have equal spacing modes using these assumptions and still have a room that doesn't sound good, and you can have non-equal spacing modes and have a room that sounds good. So it's almost like when the Wright brothers, after 2 years, realized that their foil calculations were wrong. They were using someone's calculations. They had to go back to square one and invent them all over again, which is basically what happened with us, okay? And there are not countless, but a number of programs out there. You put in, you've all used them. They're free on the internet, and you put in the width, length, and height, and you get all these modes piling up, and you start changing them, and they get equal. But they don't necessarily give you, as Peter said, they don't give you the energy, and they don't reflect the position. And at the end of the day, that is all that counts. Okay, it's the room range, the room dimensions, but where's the speaker and where's the position? Okay, and it doesn't matter what the room dimensions are. If you're in the middle of the room, you're going to have a problem. Doesn't matter, no matter what any of those formulas say. So, continuing, and that started this adventure.
Yeah, thank you, Joe. So as you can see, there are 3 assumptions in using that formula. The room has to be cuboid, because that's the only way you could do an image model.
Right.
The boundaries have to be perfectly reflecting, and in acoustical terminology, we call that the admittance. And the admittance is 0 for a perfectly reflecting room. The sound just does not get admitted into the boundary. And then lastly, the sources and receivers have to be in these opposite diagonal corners, because you have to understand that the modes that are excited are determined by where the source is located. And the modes that we hear is determined by where we're sitting. So in order to excite all the modes, and in order to hear all the modes, you have to be in opposite diagonal corners. So we start out with a comparison between dimensional ratio calculation, which again does not provide information about the energy. And as you'll see down in the finite element analysis model, where the admittance is 0, you can see the source and listener are in opposite diagonals. You see that there is a very good alignment in the frequency of the modes. And that's true because it's a cuboid room. Now let's step further, and let's introduce some admittance to a wall. If you've got a project studio Your walls are not perfectly reflecting, okay? So you've got base absorber walls, but you don't know what they're doing. And so this is an admittance that we use typically in the studios that John designs, where you have gyp, plywood, gyp. So you can see that everything is different. The higher admittance broadens the resonances. And then let's introduce
Position.
a loudspeaker into the room. We have a totally different situation. And then finally, let's introduce the listener into the room. And we get an enormous null because you're sitting in the middle of the room. That's the first width mode, first width node, null. So are the dimensional ratios important? A little bit.
A little bit.
They're not necessary and sufficient. That's a scientific term that we like to use. Now, what you're seeing here is possible because this is a wave solution. What you're seeing is the pressure map on the left is just the main speakers. And so you're seeing the pressure distribution at the various frequencies up at left. In the middle, we have just the subs. And so you have a different pressure distribution. And then at the right, we have the mains, the subs, and a few additional woofers, subwoofers that we had to actually add, which is what we had to do at Rue Boyer, because as John was mentioning, the geometry was relatively fixed. So to control the low frequencies, we had to do that. So what is the problem? The problem is that we have to optimize the geometry simultaneously, the geometry, the source position of the speakers, and the location of the listeners. And there could be multiple listeners, there could be multiple loudspeakers. So that the pressure is uniform at all of the frequencies. It's almost an impossible task to do manually, which is why we have developed an AI engine. And how we do that is with a program that we call Nero, and it stands for Non-Cuboid Iterative Room Optimizer. And all that means is that the way the room optimizer was just for cuboid rooms, we can now handle any shape room. And it's an iterative process because there are so many variables that you cannot manually evaluate them all, and you had to iteratively search among the various possibilities until you reach a conclusion. And the conclusion is another thing that we will talk about. So you have to simultaneously, you could read it as well as I, optimize all of those variables. You have
Go back to those three assumptions. Cuboid room, zero admittance, and everybody's speakers and listeners are in the corners. None of those conditions usually happen.
And now, in a wave acoustic analysis, we have to use something called complex terms, which are the magnitude and the phase. The admittance is the reciprocal acoustically of the impedance. And so we have to use complex admittance for the boundaries and for the treatment that we put into the room, as you'll see. We use FEM below 200 hertz, that's a wave model, and we use the image source model and ray tracing above 200 hertz to determine the location of the specular reflections and also to determine the reverberation time of the room. And we use what is called, it's a tongue twister, a non-dominated sorting genetic algorithm. All that means is that it's an AI engine, because what we have to do is we have to optimize 4 variables at the same time in such a way that we get a compromise solution. In other words, we don't make number 2 really good by making number 1 have a poor response. And so we have to evaluate thousands of solutions, as you'll see, until we come up with a compromise solution using this AI search engine. And these are the 4 objectives, the objective metrics that we're going to optimize. The frequency response, you're all familiar with the fact that you would like a loudspeaker to have a flat frequency response, because if it didn't, it would color the sound. Well, the same thing occurs for a room. If the room does not have a flat frequency response, it will color the sound. And you'll have to equalize that coloration, and then when you take it out of the room, you're going to get the reciprocal of that equalization. So below roughly 200 hertz, it's called the shorter frequency. It's basically given by the square root of the reverberation time over the volume. And we use that wave equation optimization to, again, optimize the frequency response and also the speaker boundary interference. Then moving above that shorter frequency, we use the image source model to determine the location of the early reflections. This is where you would put absorbers and diffusers, and also to get the reverberation time of the room.
So I want to hang on this one just for 2 seconds.
Yeah.
This is the only bit of math you kind of have to follow. Just look at the equation for the Schroeder frequency. That's the frequency where these two worlds change, okay? And without understanding how we got to it, look where volume is. You can, without too much work here, you can see that as the volume gets bigger, there it is on the bottom of the square root, the Schroeder frequency is going to get smaller. So when you're at Madison Square Garden, you don't really have this problem. The first eigentone, the first moment where you're dealing with this could be 2 hertz. You're not even hearing it, which is why small rooms are actually harder to deal with than large rooms. They're cheaper, but they're less expensive to build, but that's just because they're smaller, okay? So as the room gets smaller and smaller, this Schroeder frequency gets higher and higher, and it gets more in your face, okay? Once you're over the Schroeder frequency, remember I said it in simpler terms than Peter's presenting it, it's not that complicated. It's ray analysis, or what's called specular analysis, and pool ball hits the wall, it bounces off, reverb time calculation, pretty well known, et cetera, et cetera. And this started out as a low frequency optimization tool. That was really where this project started, and then we added the high frequency afterwards. But whoever says small rooms are easier to conceive and design is wrong. It's just exactly the opposite. And we are in the era of small rooms.
Very small sometimes.
Very small rooms, including bedrooms.
So 4 objective measures. The first objective measure is the frequency response.
Yeah.
So the dotted line is the response in the room before any optimization is carried out. Okay, so you see the modes. The peaks are the modes. Now, interestingly enough, we can treat some of the peaks, but we cannot optimize the valleys. So the first step is to
get the peaks down,
raise the valleys. And the solid blue line is the frequency response after treatment. And then what the light blue area is, is how the frequency response changes as you're mixing. You might mix over here, you might get tired and move over here. So we want to get the spatial deviation to be as small as possible. So
you're going to see this Schroeder frequency line. This changes for every room, which we immediately find out. This represents a pretty typical small room, 200-300 square feet, 4,000 cubic feet, et cetera, et cetera.
So the next objective measure is what I've called the reflection-free zone. Now that all started with the fact that when you're in a large room like this or a concert hall, there is a time delay between the direct sound, which is the first peak you see there, and the first reflection you hear. And you think about it, you're hearing my direct sound, but it takes a while for the sound to bounce off that wall and come back to you. Now, we don't have that in a small room because the walls are so close that we now have interfering reflections from the sidewall, the floor, the ceiling. And in order to create a reflection-free zone, we have to get rid of those reflections. Now, we also have a problem in the rest of the room because we have this sparse reflection pattern. In a concert hall, what you have is the pattern that we show down below, diffuse reflections. And of course, in a larger room, that time scale would go out to 3 or 4 seconds. Now, how much we have to reduce the level of those specular reflections in the reflection-free zone is determined by psychoacoustic analysis. And so you have a threshold, you have a spatial impression area, and then, of course, you get into a region where the reflections are disturbance. They create an interference. So we typically want to reduce those reflections down 20 dB, 30 dB if we can. And you can't accomplish that with porous absorption alone. We have to couple the porous absorption
with geometry,
with a geometry change. We have to splay the walls out. So if you look at the footprint of control rooms in the magazines, you'll always see the fact that the side walls are splayed out, and if possible, the ceiling is splayed up.
This is the reason why a lot of rooms are not rectangular, not because parallel walls are bad. There's nothing wrong with it. It's really to deal with the first reflection.
The next objective measure is the modal decay. And again, there are psychoacoustic measurements and analysis carried out where what the level of the modal decay is acceptable, when it's offensive, and we want to get the modal decay as flat as possible so that all frequencies decay at the same time. And then, of course, we want to get the reverberation time in the room within those dotted lines, which are standards that the industry has set up. And we want to do that all simultaneously. So the first thing we do is in this geometric optimization module, we have two: geometric optimization and then the acoustic treatment module. Because we have architectural constraints, we basically take the vertex of each of the corners. This is a symmetrical room, so we're only looking at one side, but we have a volume in which that vertex can move, again with the second vertex, forward and backward, in and out. And so we have constraints on how wide the room can be and how narrow it can be. And also where the loudspeaker can range and where the listener can range. And so in the Nero module, we have an iterative AI engine basically looking at hundreds or thousands of possible geometry, where the geometry is changing. As the geometry changes, the source position changes, the listening position changes, and simultaneously, that's why we have to use this non-dominated sorting genetic algorithm, because we don't want to make the frequency response good if the spatial deviation is bad or if the reflection-free zone is not free.
I'm going to interrupt for a second. Somebody should have or could have said, well, what comes first? What 99% of the time comes first? Actually, I'm going to say 100%. We have to start with some design. Somebody's got to start with, here's what the shape of the room that we want, and here are the variables that can happen. The height can grow by 2 feet. The width could grow by 2 feet. The width can't grow. In the case of Rue Boyer, very little could grow because we inherited an existing room, okay? The listening position could move by 10 inches or 1.5 feet, et cetera, et cetera, et cetera. So we start with the design. Why? Because that's generally what happens. And where does that come from? That comes from programming, that comes from a client, it comes from a site, it comes from all kinds of things, okay? Then the work happens. So what do you start with first? You got to start with an intuitive design. So if you start with an intuitively correct design, what might that be? Well, it might be a design you used before, or one that you know works. In the case of, that's how we do it, or that's one way that we do it. You're going to be better off. So if we hand this program a cube, for instance, and we tell the program you cannot change any of the dimensions, and the listener is in the middle, and we can't change where he moves, we're not going to get a very good result because we haven't allowed the program to do anything. Okay, it's pretty bad to begin with. And okay, on the other hand, if we start with a better shape and the more variables we can give the program, the better. Okay, and then what it comes back with is interesting. The program sometimes come back and says lower the ceiling. Then the client says I don't want it lowered, I want it higher, et cetera, et cetera, et cetera. And then the fun starts. Yeah. Okay, then the fun really starts. And we do have job security.
So we're at that position now, right? We have done the best we could.
Best we could.
With the geometry, maybe not even the geometry, and the only thing we have left
is treatment.
Is the treatment, and possibly additional subwoofers. So the different treatments that are typically used are resonators, porous absorption, and diffusion. And now the resonator could either be just a resonator, or it could be a hybrid resonator, meaning that there could be something on the face of the resonator, a porous material, or a binary amplitude diffuser sheet. And so what we have to know about that resonator or hybrid resonator is the transparency of the fabric, if there's fabric, what the expo panel might be, what the hole diameter spacing and spacing are, how much porous absorption, what is the flow resistivity of the absorption. It's a tremendous difference, whether it's R19, something really fuzzy, or it's R9 or R7 or 6, which is a little more rigid. And then we have the depth. When it comes to porous absorption, again, the fabric covering, the transparency, the porous absorption, the thickness of the porous absorption, flow resistivity. Comes to the diffusion, the bandwidth of the diffuser, where we're going to locate it.
They're going to push us out in a few minutes, so we got to get.
Yeah. So, and then here's the search engine. As you change the acoustical treatment, what the program is doing is calculating the absorption spectrum.
So first step, optimize geometry, then start with treatments.
And then, so we use a transfer matrix prediction for the absorption at low frequency, but we also measure it against in an impedance tube. This is a 25-foot long, 7-ton impedance tube where we're measuring a resonator there, and we're comparing the transfer matrix with the measurement. And so far, we have a very good accuracy. And then we get into the choice of the absorption. We have so many choices. In a 300 millimeter deep space, we have just a plethora of possibilities. Whether it's a slot resonator, a perforated resonator. So now here's what the challenge is. The architecture has dictated where we can place this absorption. We might have a 300 millimeter deep panel on T2 there, and maybe T3, but some of the other panels might be a little shallower. And so we go into the AI search engine, and now the search engine is determining for position 2, say, what is the best possible of the 63 or 100 possible choices in that location, which is the best one that simultaneously optimizes all of these objective measures. And then you goes to the next treatment, the next surface, the next surface.
So again, a little chicken and the egg. Sometimes we hand the software blank treatment locations. Why? Because the architecture dictated it. A window, a column, look and feel, a bookshelf, etc. Other times we let the program say, this is really where you should have the treatment, and then we see if we can do it. Whoops, it's in the way of an air conditioning duct, or we need a light there. So it depends, and that's, again, where the fun is.
Okay.
Are you guys, do we have the next panel already?
We are going to go till right to the limit, okay? We got another few minutes?
Well, we have a pretty big changeover, so.
We're going to go 4 more minutes, skip the questions, and then we can go questions afterwards, okay? Let's just, yep.
Okay, so John is going to talk about some simpler solutions that we have here.
Well, I just wanted to, I would say the room that we spent the most, that we've had, well, I shouldn't say the most success was the Rue Boyer studio. Some of you who were here earlier will remember it. And that picture there gives you an idea of how, I mean, when you look at the photo, I kind of held this out in the first part, that's how many different treatments are in that room. But I think proof perfect that you don't really think these are treatments. I mean, with the exception of maybe the resonator in the back, okay? They don't have to be aesthetically unpleasant, okay? And that was the challenge. There were about 11 or 12 different kinds of treatments to optimize this room. This was a room where we couldn't change the geometry, very, very little. We could change the position of the speakers, and we could change a little bit the position of where we sat, but not much, because that elevator pit was already there, okay? There's some more pictures of it. And then, of course, for those of you who aren't here, and the console that goes down, and we even got to use that volume. This was a real acoustic asset to be able to use the volume, because that's a great location for low pressure buildup, is right underneath the mixer. Okay? And going down. And then, of course, when it's down and it's covered, it's a studio. Here are the results of that room. There was a giant mod fractal, or third generation mod diffractal in the back wall, one of the biggest we've ever done. So this is the above Schroeder frequency work, and here are the results. These are sterling results, simulation versus measurement. These are very, very close. In our world, these are right on top of each other. And for those of you who've been taking pictures of these slides, you're working much harder than you have to work. I just give you the PowerPoint. Okay. I don't know why I just give it to you. We're happy to share it with you. We want you to have this. Okay? Again, simulation versus measurement. Spot on the money. And these are our T30 or reverberation time. Okay, notice no big, giant, low frequency rise. This is the biggest single problem in small rooms. You look at a small room, boom, it goes up. I know immediately no low frequency absorption. So how do you expect your low frequency to respond correctly? Anyway, a good way to end, this is just the beginning. If this is interesting to you, please visit. We have a booth here, and Peter's here all day tomorrow, and we'll just dive into the NIRO software and the sort of science behind it. We'll go as deep into the pool as you want to go in.
What would be the name of the booth?
Well, WSDG. Just look up WSDG. We have a booth, and right behind it, NIRO is there at the symphonic booth. We're right next to Mix with the Masters. Thanks. Sorry about no questions. Okay.